Okay, so a couple of things, like when you get to that question about Diane and she's sending a text message, okay? So the first thing you got to do is convert the kilometers per hour into meters per second, okay? Now, some of you are going completely overboard with your significant digit, like way out of control. So you have 70.0 kilometers per 1 hour. Okay, if there's a decimal place, you count to the right. So that has 1, 2, 3, that has 3 significant digits. So when you do this conversion, and you go, oh, 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds, okay? Multiplied by 10, divided by 36. So when you get this number of meters per second, make sure that you keep at least 3 digits in that answer, okay? And that in meters per second should be something close to your age, okay? Something close to your age. Then you're going to travel, and that's going to take you 1.75 seconds, like 1,001, 1,000, that's about how long it's going to take. And you're going to figure out how far you're going to go. Your answer to number 5 should be in the mid-30s, okay? Not something times 10 to the 6th that somebody might have gotten, okay? So that's about 1/3 the length of the football field. So this is why when you're driving, it's so important that you don't get distracted. Because this is only going 44. You're not out on the highway, okay? You're going 44 miles an hour. You look down, 1,001, you have traveled 1/3 the length of the football field during that time, okay? That's why I gave you that problem. So if you're looking, oh, I'll just glance at my phone. Well, when you just glance at that phone, and again, this is only going 44 miles an hour, you're going to go 1/3 the length of the football field during that time, okay? So if you get the urge to look at your phone while you're driving, don't, okay? Don't. All right, now let's talk about all of number 6 in its entirety. So at number 6, here's the rocket. Now, don't make this complicated. What's the initial velocity of the rocket? 0. Okay. Now, don't confuse acceleration with velocity. They are not the same thing. Are they related? Yes. But velocity and acceleration are not the same thing. So, the initial velocity of the rocket is 0. It's like it's sitting here. You're going to fire those rocket engines, and it's going to be going faster and faster and faster as it goes up. That's the whole point of the rocket engine, okay? So your velocity time graph is going to start here, okay? Initial velocity is going to be 0. Cool. Now, there's a couple of ways you can view this. I'm going to explain it in 2 different ways. One option is that you look at the slope of a velocity time graph. What does the slope of a velocity time graph give you? Acceleration. You have the acceleration. That acceleration is 5 meters per second squared. Now, if you're a slope kind of person, what that means is that for every second that goes by, your velocity goes up by 5 meters per second. So if you start at 0, at the end of 1 second, you're going to be going 5 meters per second. You go another second, you're going to be going 10. At the end of 3, you're going to be going 15. Because acceleration, remember, does not tell you how fast you go. It tells you the rate that your velocity changes. Okay? Big difference between the 2 of them. It tells you the rate that your velocity changes. So you're going to fire this thing for 8 seconds. Now, if you like a monetary example, okay, if you like a monetary example, imagine that you have a job, and don't lose this job because it's a sweet job. You have a job that pays you $5 a second, okay? That's your rate of pay. You get paid $5 for every second that you work. Excuse me, that you work. At the end of 1 second, how much money have you made? $5. You work for 8 seconds. You made 40 bucks. You want to make 40 bucks, work 8 seconds. Not bad. Okay? Not as bad as I'm telling you. If you ever get that job, remember your physics teacher, I'm just saying. So, you've worked 8 seconds, you made 40 bucks. So what that means is the end of 8 seconds, this thing is going 40 meters per second. So, imagine I'm here. I'm going to start, I'm going to throw this up, it's going to go faster and faster and faster. At the end of 8 seconds, this thing is going 40 meters per second. Now, when we get into forces, I'm going to give you a quick precursor into forces. When you get into forces, there's 2 forces that always work against you if you're on Earth. And I've referred to them as the mafia. So there's 2 different mafias that we're going to talk about. The gravity mafia and the friction mafia. Okay? So the gravity mafia is always trying to hold you down. If you want to make something go up in the air, you have to pay off the gravity mafia. So what's happening to get this rocket up in the air, you had to go to Big Tony, with the local branch of the gravity mafia, and go, hey, Tony, I need to launch a rocket. Tony's go, you good boy, you good boy. You're paying me so much money, I'll let you launch the rocket. Okay? So you have to give Tony a certain amount of money to get the rocket up in the air. So at this point, you've paid off Tony long enough to fire the rocket engines for 8 seconds. But then you've run out of money. Now Big Tony's going, you good boy, but you're not paying me no more. You gotta shut down your rocket. So you shut down the rocket. Tony, the gravity mafia, is gonna kick in and go, I gotta shut it down now. So as soon as I shut off that rocket, what's the rocket gonna begin to do? Speed up or slow down? Slow down. Slow down. So now, because the gravity mafia is the only thing acting on the rocket at that point, now, and don't confuse motion with velocity. The rocket is still going up, but it's slowing down as it goes up. So that's like me throwing this up in the air. It's still going up, but it's slowing down as it goes up. Okay? Now, this is also true of America, if you go back with the financial analogy. You earn $5 per second. Great. You have a sweet job. You've worked 8 seconds and you've made $40. Now, true of America, now you're going to spend that money. But you're going to spend the money at $10 per second. Okay, that's the rate that the money goes out. This is what makes America great. Okay, welcome to credit card debt. So, you worked hard. You worked hard for 8 seconds and you made 40 bucks. You got $40 burning a hole in your pocket. You're going to go to the mall and you're going to spend that at $10 per second. How long is it going to take you to run out of money? 4 seconds. Okay? Because now you're going to drop for every second that goes by. Now, for every second that goes by, now you're going to drop 10. So at the end of 1 second, if you start at 40, what are you down to? 30, then you're going to be down to, and then you're going to be down to 10, and then you're going to be broke. Okay? So your velocity is going to go to 0. Now, when that velocity goes to 0, where's the rocket at? On the launch pad or at its highest point?
At its highest point.
At its highest point, because that's when the velocity is going to go to 0. So, when I ask you to draw the motion diagrams, do not make these complicated. I'm going to show you exactly what I want done. If you want to draw a rocket, that's cool. You don't have to. So, I'm going to draw a rocket. Boom. I'm just going to draw some V1. I don't care what it is, just going to draw that. I'm going to draw a small little V1. So when I draw that second velocity vector, one of 2 things is going to happen. Either the velocity vector gets bigger or the velocity vector gets smaller. That's it. Those are the only 2 options that we're going to have. Going to get bigger, going to get smaller. Okay? That's it. What's it going to do? The rocket engines are being fired. What's it going to do? Get bigger or get smaller? Get bigger. So now when I draw like V2, I'm going to draw V2 bigger and then I'm going to draw maybe V3 even bigger than that. So, when you draw your acceleration vectors, and you remember this in terms of the lab today, if something is speeding up, do the acceleration vectors point in the same direction or the opposite direction? If you're speeding up, they're going to point in the same direction. That's what makes it speed up. So I'm going to come over here and I'm going to draw some positive acceleration vector. We're overcoming the gravity mafia and we're accelerating upward. Okay? So that's all you have to have. That's it. That's all you have to have for the motion diagram while the engine is being fired. Now, if I shut off the engines, immediately what's going to happen to the velocity vectors? What are they going to start to do? They're going to get smaller. Are they still going to be pointing up? Yes, for a while they're still going to be pointing up. So now I'm going to draw another one and maybe go, okay, here's V4, and then I'm going to make my velocity vectors get smaller, V5, V6, something like that. Now, as soon as it starts to slow down, which direction does my acceleration vectors point? Down. In the opposite direction, in this case, it's going to point down. So now I'm going to have some negative acceleration. Literally, that is all you have to have for the motion diagrams. Okay? That's it. Do not make this complicated. So the same thing is going to happen here on this velocity time graph. Your velocity time graph should look something like this. There's 40 meters per second. That was at 8 seconds. And that's going to take you another 4 seconds. So you're going to have a total time of 12 seconds. Okay? Now, here's the thing. If something's going to change direction, Elizabeth, there's 3 things that have to happen to change the direction. What are those 3 things?
You have to slow down, stop, and speed back up.
Beautiful. Okay, you remember that from the lab today. So when I throw the swirl up in the air, the swirl is going to go up, slow down, stop, speed back up. So this is when we shut off the rocket engines. Okay? So the rocket engines were shut off at this point. This also boils down to that big sign that says F equals ma. So when you had a positive acceleration, you had a positive force. I shut off the rocket engines. The only force left acting on it is gravity, and that's acting down. So that's why I have now a negative acceleration with positive velocity, and now I'm going to start slowing down because now they have opposite signs. So at this point, when that velocity goes to 0, where is the rocket? At its highest point, because that's when the velocity is 0. Now, as it starts to fall, what's going to happen to this line? Will this line go back up, or will the line continue to come down like that? Go back up, come back down. How many vote the line's going to go back up? Don't do that. And here's the reason why. Because if you tell me the line's going to go back up, you're going to tell me this would be cool. You're going to tell me that the rocket's going to stop, and then it's going to start speeding up, going up. Cool. Don't get me wrong. But here's the story. If something's going to change direction, and you remember this in the lab, if something changes direction, the velocity has to change sign. Positive to negative, negative to positive. Okay? If something's going to change direction, the velocity has to change sign. So this gets me to 0. This is the slowing down portion of it. Here's the stopping portion of it. To speed back up, I'm going to take this line straight down. Okay? So now I have negative acceleration with negative velocity, and that makes me speed up. So if you were to draw the graph for the entire thing, including on the way down, you would keep that line going just like that. And that's what happens when I throw Rocky the squirrel up in the air. Okay? this is the quintessential example of something changing direction. It slows down, stops, speeds back up, but it changes direction. Okay? So, I'm going to have negative acceleration once I shut off the engines because it's slowing down. When it falls, am I still going to have negative acceleration? Yeah. But now that negative acceleration in combination with the negative velocity is going to make it speed up. Okay? So when this starts to fall, your velocity vectors would be pointing down, but they would get bigger, and then I would have negative acceleration as well. Okay? So if I ask you to draw it for the entire path, that's what you would do. Okay? Got it. Good. Grand. Okay. Let me give you a hint on your answer to number 17, or excuse me, number 7. That's going to be a really big number. So your answer to number 7 should be something times 10 to the 15th. Nope. Nope. You're only off by like a factor of 100. Should be something times 10 to the 15th. On number 8, some of you are going absolutely crazy writing down answers with significant digits. So let me kind of give you a perspective on how science used to be done. So this used to belong to one of my uncles, and then he gave it to me on his patent. So this is what's known as a slide rule. Okay? So this is how math used to be done. If you ever watched the movie Apollo 13, and once the accident happened, they were trying to redo the calculations. If you look carefully, and this was in the early 70s, guys were still using calculators, or at least slide rules to do calculations. It's cool. If you know how to do this, you can multiply, divide, add, subtract. You can do trig functions. You can do logarithms. You can do a whole bunch of things with it. It used to be, when you were in high school, if you were going into like engineering or something like that, you would take a class in using slide rules. They literally had classes in using the slide rule. Okay, so instead of taking a class in C++ like programming, you would take a class in using the slide rule. So the limitations of slide rules is that this is why it's called scientific notation. So if you look at that distance that I gave you, 3.80 times 10 to the 5th kilometers. Okay? The reason that scientific notation works off one digit to the left is because if you were using a slide rule, I can't use the slide rule and punch in 38,000. I can't do 38,000 on a slide rule. But I can do 3.8 because you were limited to one digit to the left of the decimal place on using the slide rule. That's why scientific notation always has one digit to the left. So that way you can use the slide rule to do that calculation. Okay? Now, speaking of the moon, if you happen to be out tonight, there's going to be an almost total eclipse, not completely, but it's going to be pretty close. So that's going to start at 8:23, the moon. So what's going to happen is that here's the sun, here's our rock, here's the moon. The moon is going to begin to move into the shadow cast by the Earth. So it's going to start at 8:23, a little after 11, that's when it's going to be as dark as, that's like as dark as it's going to get. So if it's supposed to be clear tonight, so if you happen to be outside, there's that. This isn't going to happen in North America until like 2029, okay? So by then, you'll be about halfway through college by the time it happens again. So you go, man, you go 2029. I was in high school the last time we had an eclipse, okay? So if you happen to be out, and don't expect for the moon to completely disappear, but it will definitely, you'll see a very noticeable change in the amount of light on the moon. And that only happens with the full moon because we have to be on the other side of the sun. Okay, so, and even if you look at getting us to the moon, So here was the Earth, here was the moon. When they launched to the moon, they didn't aim where the moon is. They aimed where the moon is going to be. It'd be like me throwing a pass to a wide receiver going across. If the wide receiver is going across like this, I don't throw it where the wide receiver is. I throw it where they're going to be. And that's what they had to do with the moon. We didn't aim for the moon. We aimed for a point in space where the moon would intersect that path. That's what we had to aim for. Okay? It wasn't like, oh, we'll just go for the moon. If you aim where the moon is, you're going to miss it. Okay? You have to aim for where the moon is going to be. So, on number 8, here's the story. So I got 3.80 times 10 to the 5th kilometers. That has 3 significant digits. 3 days, 3.00. That has 3 significant digits. So your answer can only have 3 significant digits. So the beginning of your answers in kilometers per hour should start with a 5. Okay? So you should have 5 and some change, 3, 7, 4, something like that. And here's what some of you are doing. You're looking at your calculator and you're writing down 5347.21735 kilometers per hour. Okay? You don't have that good of data. Okay? I'm like, how far is it to the moon? 3.8 times 10 to the 5th. Okay? It's a ballpark. It isn't a laser shot. It's sketchy. How long does it take? About 3 days. Okay? I'm not saying it's going to take 521.37 seconds to get to the moon. How long is it going to take? About 3 days. You have sketchy data. You can only generate sketchy answers. Okay? So if you write this down, I'm going to think that you had the most stunning instrumentation that's ever been known in the history of humanity. Okay? No. So your answer to number 8 in kilometers per hour should be something like 5 point something, a couple of digits, times 10 to the 3rd kilometers per hour. Okay? That's what it should be. When you get to number 9, under what circumstances are you going to use a tangent line on a position time graph? And what you could determine. There's 2 parts to this answer. So let's go to your days as a geometry student. If this is a circle, what do you know about tangent lines to a circle?
Touch the circle at one point.
Only touches the circle at one point. So I could draw like a tangent line there. I could draw a tangent line there. I could draw a tangent line there. Now, obviously, you can only draw tangent lines to curves. Could you draw a tangent line to a straight line? No. You can't draw a tangent line to a straight line. Doesn't make any sense. You can only draw tangent lines when you have curves. Now, this is asking about a position time graph. So let's say that you have a position time graph and you have the bottom lip. Okay? If you have the bottom lip on a position time graph, is the object speeding up or slowing down? How do you know?
Slope is getting more steep.
Slope is getting steeper, right? So what that means is that I could draw tangent lines. So first condition, when are you going to use it? When you have a curved line on a position time graph. Or you could say when the velocity is changing, or when the velocity is non-constant, or when you have accelerated motion. There's a whole bunch of different ways you could articulate that. Then it says, what could you determine? Okay, so when you draw those tangent lines, what you're finding is the velocity at a specific point in time. Okay, technically it's known as instantaneous velocity. If you've read the notes that I gave you yesterday, that clearly lays that out. If you haven't, I suggest that you do that. So the only time you draw tangent lines on position time graphs is when you have curved lines. Now, on the lab that you're going to do today, you're going to draw a position time graph And when you get done, it's going to look something like this. Okay? When you get done, trust me, this will make sense later on. When you draw that position time graph, that's what it should look like. So if you come up here to that relative maximum and you draw a tangent line, what's the slope of a horizontal line? 0. So on your position time graph that you're going to draw for the lab, it'll make sense later on. At the very peak of that line, that instantaneous velocity is 0. Because the three things that have to happen to change direction are you slow down, stop, and you speed back up. So at the top of that line, top of that curve, when you draw that tangent line, that's when that slope is 0. That's when the cart has changed direction. Okay? Cool with that. Your answer to number 10 should make a really, really good weighted GPA. Okay? Really, really good weighted GPA. Now, there's a couple of ways you can work number 10. Okay? One option is that you can go distance equals velocity times time. You can do this with constant velocity. Okay? So you want to find time, so that's distance divided by velocity equals time. You have a distance that's in kilometers, you've got to change that into meters, you have a time that's in meters per second. So if you're into equations, do that. Here's option number 2. Burkham, I love ratios. I was president of the ratio club in high school. Cool. So I've given you 3.3145 times 10 to the second meters per 1 second. That's what that means as a ratio. It means you're traveling about 330 meters in 1 second. That's what that number means. Now, if you set it up as a ratio, you have the distance that you need to travel, which is 1,609 meters over X number of seconds. So you can set it up as a ratio and go, oh, if I travel this many meters per 1 second, I need to travel this number of meters in X number of seconds. So then you can cross multiply and divide. Now, here's the beauty of the ratio, because it tells you if your answer makes sense. If I'm traveling about 330 meters in 1 second, and I need to travel 1,600 meters, what do you know about your time? Is your time going to be bigger or smaller than 1 second? Bigger, because I have to travel more than 330 meters. So the beauty of the ratio is that you can look at it and go, right, my answer has to be bigger than 1 second because of the fact that I travel more than 330 meters. So that way you can look at your answer and go, hey, does it make sense? Okay? There's a third way you can work this problem. Third way you can work this problem is as a geometry problem. It's like, okay, this doesn't have anything to do with geometry. This is velocity and time. Sure, this is a geometry problem. I'll show you why. If you were to draw this on a velocity time graph, the speed of sound is going to be a constant line. Okay, 330 meters per second. That's what you've got. That's the height of the rectangle. You know how far it travels, which is 1,609 meters. That represents the area of the triangle. It's a geometry problem. Area equals length times width. The area is the 1609. That's the area of the rectangle. The height of the triangle is the speed of sound. The base of the triangle is your time value. That's the one that you don't know. So I don't care how you work this problem. You can work it as an equation, E equals dt. You can work it as a ratio. You can work it as an area problem. I don't care. Pick one. So your answer to number 10 should be a really, really good weighted GPA. Your answer to number 11 would make a horrible GPA. Okay? Not so good. Okay? Not so good. When you get to number 13, you've got this graph that looks something like this. Okay, and you got some blue. So you make sure that you put arrows to indicate when it's speeding up or when it's slowing down. So you're starting at 0. What are you going to do if you're at 0? What's the only thing that you can do? Speed up. So you can put like an up arrow there. Then from here to here, I am slowing down. But this is the most common mistake that's made. Elizabeth said we need to do 3 things to change direction. And you remember this in the lab today. You got to slow down, stop, speed back up. You're slowing down. When you cross this axis, what's your velocity? 0. After you cross 0, what are you going to begin to do?
Speed up.
Speed up. Do not keep putting down arrows here. You can't go slower than 0. Okay? I've seen freshmen try. Freshmen can't even do it. So what you need to do is go, oh, I'm going away from 0 meters per second. That means that I'm speeding up. So do not keep putting down arrows. Once you cross 0, you begin to speed up. Okay, most common mistake that's made. We're cool? Any questions? Yes?
Can I have that paper, please? Thank you.
Okay. Now, do me a favor, since everybody's kind of settled into where you're sitting,
Negative acceleration.
on the table in front of you, you have a number
It's
that's
just
in
up,
blue.
speeding up and down.
Okay?
It's like-
I gotta fill
Has
out a
nothing to do with
seating
the
chart
car.
just in case, God forbid I'm ever gone, which always sucks, but just in case. So, whatever blue number is where you're sitting, put that at the top of this paper. That way I can fill in the seating chart. Okay, it's just gonna make it easier than me trying to remember who's sitting where. So, you have like a number, like 9, 10, 11, whatever that number is. Okay, so put that at the top of this assignment. Somewhere circle it in something so that I can see it. Staple that graph to the back. Get that handed in. All right, stop the camera for a second.